Hey there, it's been a while. I want to go back to ordinary differential equations and the free fall problem, which we've already done in a previous video. And the way I'm going to approach this may seem a little silly at first. In fact, I want to title this video something like Maximum Overkill because it seems way over the top for such a simple problem, especially given that we're provided with differential equation solvers built into SciPy as it is. However, there is a reason behind that. And that reason is when we move on to partial differential equations, one of the techniques we're going to use to solve them, assume it's something like a diffusion equation. So it's the function is a function of space and time. And what we're going to do to solve that is transform the spatial coordinates, discretize the spatial coordinates, so that we transform one single partial differential equation into a whole system of ordinary differential equations, which we can pass into our ordinary differential equation solver. So as a prelude to that, what we're going to do is, again, we're going to discretize the system. And because this is an ordinary differential equation, what we are essentially doing is transforming it into a system of regular algebraic equations. We're going to break the video down into a couple parts in the linear case, the nonlinear case, and then a follow-up video because there are some potential issues that are going to come up with Python in particular in the nonlinear case. So in the interest of brevity, or at least an approximation thereof, I don't want to bore people to death with an hour and a half long video on this stuff. We're going to break it into 2 to perhaps 3 videos. The first one we're just going to do the linear problem, and we're going to review the built-in SciPy function solve IVP. Then we're going to do the discretization using what's called the Euler method, which is not the best way to solve these problems. And at some point we may do a future video on that and better ways to approach it. However, it's pretty intuitive and it works well enough for this problem, so we're just going to stick with it. But then we'll go on and use sparse matrices and linear systems to solve the same problem. Video 2, we're going to go on to the nonlinear problem. So that's going to create some problem. We just can't use regular linear algebra to do it. So we're going to do it with loops. Then we're going to go through and set up a nonlinear system, again using sparse matrices, and pass that into the SciPy fsolve function. Now, for a potential third video, there are issues with the way SciPy's fsolve handles sparse matrices. And as of now, I don't know quite a way to. Haven't figured out a workaround for that. So video 3 is going to be the nonlinear problem, performance issues, and the topics are very informatively called to be determined. So we may just end up using MATLAB to do that, but we'll see. I have to play around with it some more and come back to that. Okay, so now that we've gotten that out of the way, let's go over to the Jupyter notebooks and get going. Okay, so in a notebook, let's make this a little bit bigger. Do I want to go this big? I'll go this big for now. This is the problem we've already done using SciPy's numerical differential equations integration package. So we're just going to focus on the linear part of this problem today. So a guy jumps out of a plane at 32,000 meters. This is a high altitude free fall. A chute doesn't open. How long does it take to hit the ground? What's his position and velocity as a function of time? And we're just going to assume constant acceleration due to gravity and no air resistance. Later on, and we will go into the nonlinear case where there's air friction, air drag. That changes as a function of position as the air density changes as a function of altitude. And we're also going to later on assume that the gravity g changes slightly as a function of altitude. But for now, just the linear part. And I took the Python code that we already written and put it into a notebook because last time I think I did this in a console. So these are our imports, the linear case. This is the function that defines the differential equations. So right down here we have, let's make this a little bit bigger. Okay, down here we have acceleration. This is dv dt is equal to minus g. And the position, dx dt, the first derivative of position, or I think I called it y. First derivative of y with respect to time is obviously the velocity in the y direction. We set up an event function and set up our integration time. We run it. We plot the results. We get an event time of about, what is that, 80 seconds, a little over 80 seconds. And these are the plots as position as a function of time. It's a parabola, not surprising. And the velocity as a function of time is a linear decrease, linear increase, depending on how you want to think about it. And the slope of this line should be the acceleration. Okay, so let's move on now. So I've added some notes down here on how we're going to approach this. First of all, we're going to use a loop rather than a vectorized matrix code. But eventually I want to go on to the matrix code. As I said in the introduction, this Euler technique is really a bad way of doing these integration problems. However, it's going to allow us to avoid some boundary issues and having to fudge things at the beginning and end of integrations. So we're just going to use it, and it happens to work well enough for this. So what we're going to do basically is approximate the derivative of a function df dt as a difference between the two. So we're going to take the function at the ith plus 1 point, subtract the value of the function over at the ith point, and then divide by the time step, and that's going to be our approximation of the derivative. So if this delta t, this t I plus 1 minus ti is small, this should pretty closely approximate the derivative. So if we rearrange this, well, actually, let's do it this way. Let's write our acceleration is dv dt, and that's equal to minus g. So what we can do is rearrange, plug this into this type of form, and then rearrange it. So we can get the v at the ith plus 1 spot is equal to v at the ith, and then we're going to subtract off minus g delta t. So so we could write out our time steps like this. Our initial velocity is given as 0. So if we take that, we plug that into v1 here. This gives v2, and likewise we get all of this. And again, for the for the altitude, the y positions, it's all the same thing. So let's actually go on and code this. Let's see here. Let's go on and code it down here. So let's set up our something looks funny here. I think that should be a plus sign. Let's see here. Yeah, this is right. This here, this should be a plus sign. So let me go in and edit that. Okay, so I went in and changed it off of the recording. I doubled up on the minus sign because g is a negative. These come out to be minuses here, and then they're just pluses down here. So cool. Let us move on now, and we'll define some constants that we're going to need. So I'm just going to take a time step. I'm going to call that dt, and that's going to be equal to 0.1 for now. I want to keep track of the times for plotting purposes. So I'm going to set our initial time equal to 0. What else do we need? We are definitely going to need g, and that's going to be equal to minus 9.8. And like I said, I want to create a time vector for plotting purposes. So I'm just going to create a empty array and append our initial condition to it. So time.append, and I want to append t. So let's see, does that run? That runs fine. I am also going to create vectors for the altitude and velocity. So y is going to be np.array. And I can't spell today. Well, can I ever spell? And I'm just going to put in our initial condition here is 32,000 meters. And I'm going to do a velocity vector. I'm going to use capital V, and that's going to be np.array. And that's just going to be equal to 0. So does that run? That runs fine. Okay, let's move on now. And I think I'm going to be a little lazy and cheat here, and I'm going to do a while loop. And since we already know that it takes about 80 seconds, I'm just going to say while our time is less than or equal to something, let's call it 85 seconds, I'm going to run this loop. So I'm just going to be again lazy and use the append function for these vectors. So v is equal to np.append, and we're going to append it to v. And so what are we going to do? It's our next entry in V. So we're going to go up here and say we want the previous entry in V, and then we're going to subtract G delta T from that. So it's the last entry of V is just going to be the -1 entry of this vector. And then I already took G to be negative, so this is now a plus. This is kind of confusing. I probably should have decided on a sign convention beforehand, but oh well. So it's G times dt. And that should be good. So that should be a time sign. And I think I've doubled up on the parenthesis by accident now. So here. Okay. So now let's just do the same thing for y. So y is equal to np.append y. So likewise, this is going to be y minus 1, the previous point. And we're going to add to it the velocity at the previous point. So that's going to be v minus 1 times dt. Let's just see if it runs. So that looks like there are no typos. And okay, so that basically is our integration routine. So let us come down here and just add t is equal to t plus dt, just so we can record all of these. And we want to append this to our time vector. So time.append t. Okay, and let's put in a break that effectively functions as a root finding thing. So we're just going to break if y crosses 0, because it's initially a positive number. If it goes below 0, let's break out of this loop. So if the last element in y is less than or equal to 0, we will just break. Okay, any typos? So far so good. Yeah. So let's come down here and print out our final time. So let's print time, the last entry in the time vector. Let's run that. What's going on here? For some reason it got stuck, so I just stopped it and we'll just rerun this cell. So run, and we get a time of 80.8 seconds. And what was our result from the integration routine? It was 80.81 seconds. So we're pretty close here. Let's just plot this out to make sure that we get a parabola in position and position versus time, and a line for velocity versus time. So let's come down here, come over here, and we will do plt.plot time comma y. So that looks very parabolic, and let's make sure the velocity one is linear. So let's do a plt.figure to do a different figure. plt.plot time comma v. Yeah, and we get a nice linear relationship. Now, we've talked about loops before and avoiding them if possible, and vectorization, and this code is obviously not very efficient in and of itself because I'm using these appends, so it has to reallocate memory and move these arrays around. So this code is not very efficient as is, and it has a loop. So if we come back here and look at these equations, one thing that kind of jumps out immediately is we have a whole bunch of equations for velocity, a whole bunch of equations for positions, and they're all linear. So we should be able to rewrite this as a simple matrix equation. Hey there, through the magic of editing, this is future me coming back because I forgot to record the description on how I set up this matrix equation. What I have done here is I've taken our two independent variables, the height, the altitude, and the velocity, and I created a vector which stacked the two. So for every spatial point, we're going to have like a y1, y2, y3, and I made this for 5 points. So our time steps we'd be dividing our time interval into five steps. Of course, for the real case, this would be hundreds or thousands of steps, but just to write this out on the screen, I chose 5. So we're just stacking up our velocity or our positions, y1, y2, y3, y4, y5, and then underneath it the velocities v1, v2, v3, and so on. And I should probably note this matrix looks a little different than the one that's initially shown in the rest of the video. There was a slight typo in there, and I did catch it midway through and changed it in the video. But just in case, when we cut back to the recording, you might notice that this matrix is slightly different, and that is because there is a typo. Now with that, back to the regular video. In time steps of what, like a tenth of a second? So delta in this case would be like a tenth of a second. And so, yeah, this is the sparse matrix. You can see almost all of the entries are 0. We have entries on the main diagonal, the diagonal below it, and then we have off to the side a bunch of rows, another diagonal, and this relates the position to the velocities. So this connects these two basically independent sets of variables. They link the positions and the velocity. So if you multiply this out, in principle, if I typed it right, you should get the same equations as up here. But because this is a sparse matrix, we can take advantage again of sparse matrix algorithms and solve this problem pretty quickly. So let's actually code that up. Okay, I normally like to keep my imports all together at the beginning, but at least for the time being, I am going to put them down here. So from SciPy.sparse, we're going to import the diags command, which is going to create the diagonals. And then from SciPy.sparse.linalg, we are going to import the sp solve command. Let's see if those run. Okay, that's good. So we're going to need the sparse solve command, and we're going to use the diags command to build this sparse matrix. So let's move on. I'm going to create a variable t for time, and I'm going to use the numpy arange command, and that's going to go from 0 to time equals 90, since we know we're about 80 something seconds in. And for the time being, I'm going to take a time step of 0.1. So yeah, let's see how many entries there are in that. So n is going to be equal to t.shape, the first element of that, and let's just print out n. So that's 900 elements long. We're also going to need delta, so capital delta, and that's going to be equal to np.diff t, and that's a vector, so we're going to take the first element of it because they should all be the same. And let's just print out delta down here to make sure that it looks good. Print delta 0.1, which is what we expect because we kind of set that up here, but this is just a way to get it if you create your time vector in some different method. So we're going to have 900 elements, 900 space points, and 900 velocity points. So our matrix is going to be twice that. So it's going to be an 1800 by 1800 matrix. So let's go on to build that down here in this cell. So let's create this first main diagonal, and we're going to do that by we're going to set it to a vector of 1s that are, and then divide it through by this capital delta, and then we are going to have to go back and reset this initial value to 1. So let's start just by saying d for diagonal, and that's going to be equal to np.ones. We know the length of that vector is 2 times n, and we're going to need to divide this by delta. Let's see, does that run with no issues? Good. So I'm going to create these vectors first and then reset the values. So this next one here is the one below it. So let's just call it dm1 for d minus 1. So dm1 is going to be equal to, in this case it's a negative, minus np.ones. It is 2 times n minus 1 elements long. And then we're going to have to go through and divide it by delta again. So do I have any typos? Apparently not. We'll see if this actually runs in a bit. And then we're going to need another vector of minus 1s here. And that's going to be, let's call that, I don't know what to call that. Let's call that d sub n, because this is the nth nth diagonal. So d sub n is going to be equal to minus np dot ones, and that is n elements long. Does that run? Yes, it does. Okay, now let's go back and fix these this initial value here. So we're going to add, I'm just going to add a space in here and say d0 is equal to 1. And that should be good. Now we should be able to actually build this matrix with the diags command. Staring at this, I see an issue. Here for our initial velocity, so this I've taken five elements here, so let's go to our initial velocity. This will be like the 6th row down. When you multiply this out, this should give the initial velocity, so this obviously does not. So this here should be the initial velocity, which is 0. This element right here should be a 1, and this element here should be a 0. So I was a little too quick with my copy and paste while building this matrix. I'm going to edit this off of the recording, and then we can move on. Okay, fixed, I hope. So this is again a 1, this changed to a 0, and this corresponding value here is a 0 for our initial velocity. So now let's come back to here, and we're going to have to change the nth plus 1 element of this vector here. So d n plus 1, and that's going to equal 1. And then we're going to also have to change the element next to it to a 0. So let's do that. So that's going to correspond to this, where is it here? It's this dm minus 1 vector. So let's change that. So dm1, and that's going to be the n minus 1 element, I believe, and that has to be equal to 0. So I think we are good, and we can actually begin constructing the matrix itself. So let's begin doing that down here. Let's call that matrix, let's just call it S for sparse matrix, and that's going to be equal to diags. And the diags command is going to take an array or a list as a argument, and that's going to be dm1, d, and d capital N. So these are our diagonal elements, and then we need to tell them which diagonals they're on. So the dm1 is the minus 1, d is the 0th, and dn is the nth. And then we also need to type a format, and this is going to be equal to CSC. And that's just because SciPy has a bunch of different ways to store this matrix in memory, and CSC is just what we're going to use. Let's see if there are any typos. Nothing obvious. So let us now come back up here, and we're going to build our vector of knowns. So that's just going to be this here. So let's initially just set this all to zeros. So let's call that vector, I don't know, let's call it y. And that'll be np.zeros. And that's going to have 2 times n number of elements. Now y0 is our initial position, so that's 32,000. And so they're all zeros down to here, and then they're 9.8. So let me, I don't know, let's do it like this. yn colon is equal to minus 9.8, and then we need to set the nth element explicitly to 0. I could have just done the n plus 1 up here, but oh well. N is equal to 0. So that should be good. That seems to run, and now we're just ready to solve the problem. So let's call our vector x and call sp sparse solve. We're going to pass in the matrix S and our known vector y, and again that seems to run. So let's actually look, let's take this x vector apart and see what we have. So what did I call my time vector? I just called it t. So if we go plt.plot t comma x, and that should go from 0 to n. That should be our positions, and that should give us that same parabola as above. And it seems to do so, and we cross 0 right around 80 seconds, which is what we'd expect. And let's plot out the velocity here. So let's actually create a new figure, plt.figure, plt.plot, t comma x. It's n plus 1 to the end of the vector, is it not? What's wrong here? Is it there we go. It's the nth element. So again, we get a nice linear relationship for our velocity, and that's basically the same thing we get up here. So yeah, that's about it. Yeah, that's where I want to call it quits for the for today. This might seem overkill for such a trivial problem, especially when there are built-in solvers that can handle it more easily. But I want to, hopefully this will be obvious why I'm doing this in future videos. So I'm going to end it here with this linear case. We're going to move on to the nonlinear case in the next video, and I will see you then. And before I sign off, let me just say I found an indexing error here. I had where was it? This here, I had set to D, the nth plus 1 element. I'm kind of used to MATLAB indexing rather than Python. So that was my mistake, and I found it because there was a kink. If you looked carefully at this previous graph, there was a little kink here at the beginning. One way to kind of find some of these issues is to go back and restrict the number of data points you are using. So I changed this from 0.01 seconds to 20 seconds. That gives me 5 elements in a 10 by 10 matrix. And then I come down here when I build my matrix and I use the SciPy command, which kind of prints out a schematic of what that matrix looks like. So I had misset one of these elements, and now it's you can see that it's correct. Hopefully it's correct. So that's just a quick way to debug some of these. If something seems odd, it's often an indexing error. Unfortunately, you don't get something for nothing here, and we get a speed up in our code by doing this, but you do have to do the bookkeeping rather carefully. And this is a simple problem, and it gets a lot worse when you get to more complicated partial differential equations with different boundary conditions and such. So my mistake. I will comment this code up and put it online. So again, see ya.